for posterity's sake. All right. So when we talk about spectrophotometry, it's a great tool, but there's one caveat that can kind of be a drawback in some cases. And that caveat is that spectrophotometry really only works well if you're dealing with a colored solution. If the solution you're working with is colorless, spectrophotometry is not going to do that much for you. When we think about light, okay, like white light, be it from a light bulb or from sunlight, that white light contains all the wavelengths of the visible spectrum overlapped on one another. And so when that light passes through something that is going to absorb some of those wavelengths, then those wavelengths get subtracted out of that white light, and what we see is something different than that white light. So if we pass light through a colorless solution, that means that all of the wavelengths are making it through that solution and making it to our eyes. So colorless solutions are going to allow all wavelengths of visible light to pass through or to transmit through. A colored solution, however, is only going to allow some of those wavelengths to transmit through. And so the wavelengths that don't transmit through are absorbed. Right? They're absorbed by the chemical bonds and the just the molecular structure of the solutes, the things that are in that solution. And so spectrophotometry is going to measure the amount of light that is absorbed or transmitted by a chemical in a colored solution. That's the caveat. It's got to be a red, green, blue, purple, orange, yellow, some kind of color in order for this to work effectively. Quick aside, the difference between clear and colorless, they are not synonymous. A lot of times we'll use them together, but they do not mean the same thing. Clear simply refers to the fact that light can pass through something. The opposite of clear would be opaque, all right? So where the light is blocked. So you can have a clear red solution, okay? So like if you had a glass of red Kool-Aid or whatever, and you held it up to the screen, you'd probably be able to read the words that were behind that because that light is still able to pass through it. It's going to look red, but the light is still passing through. Colorless means there's no hue to it whatsoever. There's no reds, greens, yellows, blues, excuse me, any of those. Okay, so it's an important distinction. A lot of times we drop those terms, interchangeably, but they don't really refer to the same thing or convey the same meaning. So different substances, because they've got different bonds, different connections in there, are going to absorb or transmit different wavelengths or colors of light. So if we can figure out what's the ideal wavelength, then that's going to be the best wavelength to study that particular compound at. And so what we're going to do is we're going to use the PhET app to investigate this relationship between absorbance and concentration of solutions, see what that relationship might be, and then start to look at how can we best choose the wavelength that we should use in a spectrophotometric study. Okay, so at this point, if you scroll down a little bit on your class notebook page, you'll see the first part of the PhET lab handout. And so if you haven't already, open up the PhET app on your iPad and then get into the Beer's Law simulation. Or if you're getting onto it on a separate computer, you have the URL there. And I'm going to bring this up as well and share this screen. And the first thing I want you to do is literally just take a couple of minutes here, like you see there in the introduction, and I want you just to explore the app, okay? See what things can you turn on, what can you adjust, what can you slide, what can you move, what can you toggle on and off, just what is possible, what are the editable things that you can do in this sim. And as you're doing that, kind of keep in mind the second question there, does changing the concentration affect how much light is absorbed and transmitted through the solution? Now that's a yes or no question. So as you're coming to that conclusion of either yes or no, be thinking about why you feel that way. All right, so take 2 minutes for that. All right, so now that we've looked at the simulation a little bit, I want you to go down to the next section on your notebook page, investigating absorption and concentration. And I want you to make a prediction. So this is just from what you've already observed and maybe what your notion of concentration of solutions is and the amount of light that it's going to absorb. Make a prediction, a graphical prediction on that grid that you see there in number 1. And just draw what would that graph look like if you were going to plot the change in absorbance as you change concentration. What would that graph look like? Take a minute and sketch that out in that block there in number 1. Okay, so if you look in the simulation, again, where the solution is listed here is drink mix, click on that list. You can choose from a variety of those. Pick one of those. And then you're going to leave the wavelength set on whatever the preset is. So as you change these, that preset will change, but don't go to variable, okay? Leave it on preset. If you look in the table underneath concentration, all right, there's a line and then the big M. The big M is molarity. The line is for whatever prefix is with the concentration for that given solution. So for instance, with drink mix, it's millimolar, so little m. If you go to something like potassium chromate, it's micromolar. So that Greek letter mu looks like a lowercase u with a mullet. All right. That is the prefix that you would write on that line. So that line is just there for you to put in the metric prefix that goes with that measurement. So use the slider, use the arrows to pick 5 different concentrations, measure the absorbance at each of those concentrations. Then once you have those 5 data points, go ahead and graph that on that grid that is immediately to the right of the data table. Pick an appropriate scale. There's no absolute right or wrong as to what that scale is. But a good scale is going to maximize the use of the blocks that you have. It's a 10 by 10 grid. So again, choose your scale wisely, make it so that it's easy to plot the points, easy to find the points, and come up with that sketch. And once you get that done, okay, consider question 3. How does your prediction from number 1 compare to the data that you collected? And then number 4 is, looking at the general relationship. How would you describe that relationship between concentration and absorbance? All right, so take a couple minutes to collect that data and graph that. Claire, what did you come up with for that last question? How would you describe the relationship between solution concentration and absorbance?
I said as the concentration goes up, so does the absorbance.
Okay, so they were a direct relationship. If concentration's up, absorbance goes up. And we can very easily test that with any of these. As we increase that concentration, we see that absorbance value getting larger. We also see the color of the solution getting darker, which hopefully, in your mind makes sense that the darker the solution is, the more stuff there is, the higher the concentration, and the more stuff there is to absorb the incoming light that's coming in. All right. So it is a direct relationship. And that's what Beer's law, the Beer-Lambert law equation actually helps us to quantify, to be able to calculate what it is. We'll talk more about that tomorrow. But to kind of draw things to a conclusion for today, if you scroll down a little bit, an absorbance versus wavelength on your page here. Some wavelengths of light passing through a colored solution are absorbed more than others. By studying the wavelengths that are absorbed, we can understand the color that we see. So the actual color to the naked eye of the solution is dependent upon or is based upon what wavelengths are being absorbed. And so when we're studying a solution, the best wavelength to use for that study is a wavelength known as lambda max. So again, lambda is that Greek letter, lowercase l. It's kind of curly Q, and then it's got a straight line coming out of it. Looks like a dinosaur. It's the best way I know to describe it. I know people have different pictures of dinosaurs in their heads, but that's what it looks like to me. It looks like a brontosaurus. Anyhow, all right, we'll do more with lambda max tomorrow as far as determining what is lambda max for a given substance. And again, it's going to be different for every different material because if you look at these different solutions, they're all different colors. So obviously they are absorbing different wavelengths of light. Now, the drink mix and the cobalt compounds, they're all kind of in the red area. So you might expect that their wavelengths of absorption are going to be kind of similar to one another. But you know, when you've got as many different colors as you have here, you're going to have different best wavelengths of absorption. So here's what I want you to do, all right, for tomorrow. If you look at the bottom of the page there, okay, very next section, if you're filling things in, investigating absorption and wavelength. So what you're going to do is you're going to compare 3 solutions of different colors with the same path length, which basically means don't mess with the double-headed little yellow arrow here, okay? And so pick any 3 from the list here. Just make sure they're different colors. So they're all pretty much different colors except for the first 3. So if you're going to do a red solution, just pick one of those 3. Don't do any more than one of those 3. And so where it says solution, you can just write the formula. You don't have to write the full name in there. Solution color, that's pretty self-explanatory. And then you've got the 2 wide categories there. So in the first one, it says preset wavelength. You're going to leave the wavelength area set to preset. So you're not going to change this at all. You're going to let the simulation choose the wavelength that it's going to give you data at. And you're going to turn the light on, obviously, and you're going to record what's the color of the beam of light, what's the wavelength. It says value. That's the wavelength. It wants the nanometer measurement of that form of light that you're using. And it wants the absorbance. So make sure you click that over to absorbance and record that. Then you're going to go to the variable wavelength section and you're going to click that to variable and you're going to adjust the wavelength so that it matches as closely as possible the color of the solution that you are studying. Okay, and then you're going to record that same info. What's the color of the light beam? What's the wavelength in nanometers of that light? And what's the absorbance? Okay, you're going to do that for 3 different colored solutions. And once you've done that, then you're going to look at and answer question B. How are the beam color and solution color related to the absorbances that you recorded for each of those? Okay. And so what I want you to do is fill that table in, come up with an answer for B, okay, based on what you observed there, screenshot that and send me a message in Teams with that screenshot so that I can see that you did that and give you some feedback on what you came up with for B. All right, so that's your task for this evening. Tomorrow, I'll push out the rest of the PhET simulation activity, and we will work through that together in class tomorrow.